honored by the invitation, and hopefully I can do my department justice, because I'm a little bit surprised you'd ask such a hardware-heavy person to come speak at the computing seminar. But today I'll talk about bioelectronic medicine. So firstly, kind of a research overview of what I work on. So I work on integrated sensors, circuits, and systems. And for whatever reason, I feel like that works and feel like circuits should start with an S just to maintain the alliteration. So that's everything from integrated sensor systems in bioelectronic medicine. So doing things like lab on a chip. So doing really high throughput research experimentation. We're now working on a special type of imager that uses something called SPAD, single photon avalanche diodes. And that's actually in collaboration with the DNA memory group to help sequence the DNA memory faster. But most of my research thrust is toward bioelectronic medicine, so that includes neural interfaces, so doing something called closed loop neuromodulation, which I'll describe, and then looking at specific biomarkers to deliver patient-specific therapy. And then also, how do we make really, really small, minimally invasive devices that we can put inside the body? All right, so given that a lot of times I have to talk to different audiences, I always thought it'd be helpful to start maybe with some basic terms and definitions of what these different fields are. So in terms of neuroscience, I think that's really focused on how does the brain work, right? And it can use multiple different types of techniques, such as electrophysiology to computational models to try and answer and address those questions. All right. I tried to be a neuroscientist a bit in grad school, realized it's much harder. I wasn't quite cut out for it. So luckily I discovered a new term, neural engineer or neural engineering, that really fit my skill set kind of as a core EE person much better. And that one I tried to summarize as a question, but it's really about how do we interface the brain? How do we analyze signals coming from the brain and use them, either for medicine or for some type of prosthetic or other type of interface to the body. And so that's really seeing a lot of growth recently. You have new companies like Neuralink and Kernel with a lot of capital. They're kind of pursuing these issues 100%. And in some sense, they're addressing neural engineering problems. Some of the companies are, hey, we can make a device that has 65,000 channels. All right, that's a neural engineering problem. And we don't know yet what neuroscience questions we'll be able to answer with that. But first, we need the tools before we can start formulating good questions. But really, I think my field is kind of a subcomponent of that, of bioelectronics, which is how do we use these neural interfaces and specialized hardware and signal processing to regulate or restore function in a body. So it has a much more clinical aspect to it. And just as an overview, neural engineering, it's a very complex and multidisciplinary field, uniting several disciplines together to kind of accomplish and solve our hardest problems. So my main area is circuit design, but I also have to be very mindful of the core, say, neuroscience or medicine problems I'm trying to solve, as well as look at maybe the electrochemistry of the sensor interface, or how do we package these devices so that they work chronically inside the body. All right. So once again, what is bioelectronic medicine? Just a little bit of a more of a sharper definition. So it's just really devices that use electrical impulses to treat disease or restore function, right, by modifying neural activity. So this could be applied to several things, but if you can somehow control the nervous system, then you can actually do quite a bit. And I would say that the term bioelectronic medicine is somewhat new, but it's actually been around for quite some time. There are several clinical examples of how it's used. So one is rheumatoid arthritis. So you actually have an autoimmune condition, and we use electrical impulses to help treat that by regulating the immune system, which I think is really interesting. And so these are kind of a spattering of different examples that really the mechanisms are very, very different, yet the kind of treatment of electrical stimulation is the same. So Parkinson's disease, so a neurodegenerative disease where dopamine producing neurons in the brain die off. And what we can do is we can actually restore function, treat the symptoms of the disease using electrical stimulation. Epilepsy, chronic pain is another one that's growing rapidly, urinary incontinence, and then depression. So these are kind of all over the body, very different organ systems, or perhaps targeting directly the brain or nerves or different organs to treat the body. And so I think in terms of the research of bioelectronic medicine, there's kind of two components to it. One is linking, I would say, neural circuits to their physiological function. And then the other aspect is improving device technology. So I'm definitely more on the how do we make better technology such that we can understand how to better treat disease. So a quick little 101 of kind of the foundation of bioelectronics. So once again, the aim of bioelectronics is to read or modulate the nervous activity of the body. So here I've got a little schematic of two simple neurons. And so neurons communicate with one another using electrical impulses called action potentials. And so using that, what they do is they can synapse from one to another and actually create a network of circuits that communicate and, you know, make us do what we do right now. You know, move my arms. And one point I've heard that's the definition of a nerd is like, you know, you just think about doing something, or you just do something kind of with your motor memory, but the moment you try to think about it, you realize how complicated that coordination is. And then you start second guessing yourself. But really what are those things is those are kind of the influx and efflux of ions, so charges into these cells to create that characteristic shape, nearly sodium and potassium usually. And so what we can do is we can actually record this activity. We can snoop on it. What that really means is we're looking at these flow of ions to create electric fields, and it can turn that into electrons, which, hey, we can then store in a computer and do all sorts of analysis on it that we want to. And so conversely, that means that, hey, we can do the opposite as well, as we can convert electrons and manipulate this flow of ions to kind of change what these circuits are doing. So that's a very simple premise of how it works. It gets far more complicated, especially when you consider the circuit level implications of what's going on. But that's the general idea. And once again, in terms of the hardware, here are a few different examples. So we have deep brain stimulators to treat Parkinson's disease, spinal cord stimulators. This is from Nevro, which uses like a array of electrodes in the spinal cord, stimulates there to alleviate chronic pain. Of course, the pacemaker has been around since the 50s. And then the vagus nerve stimulator, which is used for either rheumatoid arthritis, or I think this one's for epilepsy itself, right? Also heavily explored for depression as well. All right, so I think a lot of times the most powerful way to do it is just to show what it can do. So here's a video of Andrew Johnson, no relation. Well, I've muted it, we don't need the sound. So he was diagnosed very early with Parkinson's disease. So here you can see he turns off the device. He is immediately symptomatic of the motor symptoms of Parkinson's disease. And he's pretty good natured about it. He says, I think he's like, I'm doing the roll wave and shaking a quality cocktail with the other hand. All right. Okay. All right, so that was the device off. And so here he turns the device back on. And just pay attention to his hands. He raises them. You know, it's perfectly steady, right? Full control. I cut it off a little bit early, but then he goes on to do kind of tap test just to show that he is significantly improved, and the way a clinician would score him in terms of Parkinson's disease would be very different, right? So very clearly, this can have kind of an immediate effect in terms of the treatment, right? Unlike maybe traditional pharmaceuticals. All right. But, you know, in some sense, that's maybe a unique case that doesn't always happen because there's still lots of room for improvement. Things that you don't see is how long did it take them to figure out how to stimulate in that particular way to get that to work, right? The answer is a long time. There's a lot of trial and error programming, a lot of variations in what he's doing, other medications he's on, and what his diet is. And so the other aspect is too, that device technology that he's using, you notice it's really all stems from that basic cardiac pacemaker design, right? It's this big thing that's implanted in the chest, uses these long wires that go up through the neck and into the body. And it's been like that since 1997, since it was first FDA approved. And so, yeah, there's some medical barriers why we can't just kind of quickly innovate, but really we need new technological solutions. All right, but first of all, why is it so big? Because that's the first, why don't you just make it smaller? All right, well, let's see what it's doing. So here's kind of if you open this thing up, what you see is there's some complex circuitry inside there that will do, that will facilitate the stimulation. It has some memory and some very rudimentary communication. All right. But one thing is largely it's a battery. So there's a large primary cell battery in there, super high density to make sure that this works for 10, 15 years. And then also one more circuits thing, they have to put these large capacitors in there to make sure it stays safe. All right. That's really going to limit how many channels we can have. And then of course the long leads, which I mentioned earlier, are actually the primary source of failure. Right? These can get kinked, they're going through multiple body systems, so a major source of failure and infection. And then there's stimulation artifacts, so crosstalk from the stimulation onto any type of sensing we're trying to do. So if we really want to like sense a patient's brain state, well, it's really hard to do that at the same time you're delivering this electrical stimulation. And then telemetry. So that can pose some security risks and also additional power consumption. If you're always trying to communicate with the outside world, right, that's burning a lot of power, right? So it's not really a good solution. So all of these things are things that we need to save or fix for the next generation of bioelectronic medicine. So really what my vision is, and I don't know if it's exclusively mine, but is to take these devices and really to shrink them down such that they can be, injected, that they are nanoliter scale devices that can be placed directly at the site where they need to go. That way they can be maximally effective and minimally invasive. Right. And if you read about bioelectronic medicine, they say, oh, like something like this, as small as a grain of rice. However, I think it's actually going to be smaller than that. That's where we need to trend toward. So toward that vision, we need different solutions. So one, we need to figure out how to get rid of those capacitors. I won't talk about that a whole lot today. So that's even too much circuits for the EE department probably. But yeah, to get smaller and more channels, that's what we need to do. We need to be able to get, to record and stimulate at the same time. And if we can do that, that will enable closed loop therapy, such that we can do, sense something, compute a target state, and then deliver the right therapy for that, right? And then we need new solutions for wireless power and data, right? Because that's really a big one. That's how we're going to eliminate the battery, right? Or somehow shrink it down significantly. And then we also want to get rid of those leads, all right? Because that's really our number one target. Right? So I'll discuss a couple projects here. The first one is a closed loop chip to enable artifact-free neuromodulation. And I'll just ask you to take my word for it about safe stimulation. I'll focus mostly on the artifact rejection. So here's an example device in the market right now called the NeuroPace RNS, responsive neurostimulation for epilepsy. And so what it does is it will sense a seizure, so abnormal, aberrant neural activity, and then it will stimulate. And actually, even on this one, you can see that they don't record while they stimulate because that's their solution. They can't sense anything. So they detect a seizure, deliver therapy. And they do this in kind of an open loop fashion, or actually call it responsive, because then they have to wait a while after they stimulate before they can start recording again. So this might be okay for epilepsy, but for other conditions, we probably need something that's a little bit more adaptive and can close the loop, right? So, so that means kind of the devices on the market are not able to stimulate and sense at the same time. All right, so what's really going on here? So if you were to look at kind of a voltage recording of what this thing would be sensing, is that you have these stimulation artifacts here in the blue, and then you're trying to detect some very small biomarker shown by this green signal. And there's about 100 dB of difference in the signal powers. So, just to give you some concept or context of what that would be, it's like, trying to hear somebody whisper, when you're right next to a jet plane taking off. All right, so this is a very, very hard problem. All right. So where does this come from? Well, it's really just caused by, as you stimulate with this current across the electrode, it generates a large voltage drop. And then for, I guess, reasons I want to expand upon, you actually do need kind of large currents because, you know, the electrodes might be far from the target site, right? So, but that's kind of a different conversation. So once that current goes through the electrode, right, which we can model with this kind of simple circuit here, it creates large artifacts that will crosstalk onto our signal. And so I guess in prior work, we went through and we kind of modeled this in detail of like, okay, if you have these electrodes, you know, what actually is the artifact that you would see? And the way I describe it is that there is a direct artifact due to the instantaneous flow of current through the electrode that can be very large. So this is typically the thing that's, you know, that was the blue signal that you saw before. It's on the order of volts. Well, the thing you're trying to record is microvolts. And then there's a residual artifact, which actually is a consequence of the performance of the circuitry itself. If there's a little bit of mismatch, let's say between those pulses, okay, it seems like a very small error, 1%, whatever. But once again, think of the signal you're trying to record and it creates this really slow decay, right? That's, you know, on the order of millivolts, so still 1,000 times larger than the signal you're trying to record. All right. And one of the things that we did here is that we like, okay, we want to be a little bit more exhaustive in our understanding and modeling of this. And so what we did is we built a portable model that would let us co-simulate our circuitry and the effects of the electrode and the tissue it's in at the same time, so that we can actually co-design these things. So here's kind of just an overview is that we wanted to make it simple, so simple that even I could use it, you know, not just my students, specify things in MATLAB, and it will automatically generate a circuit that I can then simulate in SPICE, right? And get an understanding of how it works. Right? And just kind of an example here is what we did is we just created a mesh, we stimulate between two electrodes, and that will actually let us examine how the artifact changes in time and in space. Right? And for example, why is that useful? I'm going to say interesting, but it may not be interesting to you, but it's useful to me, right? Is we can now understand, okay, how do these, say like these red dots, which represent maybe victim channels, how will they sense an artifact? And so what this really does is we can then understand, all right, this is how the electrical, the stimulation artifact will look at all these different electrodes across space. And really easy to see how this is going to be a consequence of whatever our experimental or device build is. And so just kind of to distill kind of the outputs of that work is one thing that we see is that the stimulation circuitry architecture and performance really matters, right, in terms of what that artifact looks like. So what the consequence of that is that means that we can actually design it to minimize the residual artifact for these systems, right? And this is kind of obvious, but we just wanted to state it, is that it is a function of the electrode properties. So it's anything from its geometry, you know, its materials and size and placement, it really matters. But on the other hand, it is, I would say, kind of deterministic. It's something we know, right? That we, let's say if we can measure the impedance of an electrode, we can determine how much or what that artifact will look like. And then it also varies by electrode location. So it's going to be different for kind of every victim channel that we're sensing from. And the other thing you'll notice is that the artifact, while like, you know, its amplitude is huge, it is relatively low duty cycle for all these therapies, right? That they're typically on the order of, you know, 1%, right? Usually less than 5%. But it will create kind of this wide band artifact because it's an impulse and will contaminate all frequency bands. And so that probably means we should really consider more of time domain cancellation techniques rather than some type of a frequency domain cancellation. And then lastly, that the direct artifact is often just too large to efficiently digitize, right? This is several volts and the signal you're trying to record is microvolts, right? So you need greater than 100 dB of dynamic range. That's a lot of bits. right? And so this has several consequences. I don't think you can really record it efficiently. And then also you need to make sure that your system can withstand or recover immediately after one of these stimulation events. So I'll quickly walk through some of the state-of-the-art approaches. So I think one that's kind of very straightforward is just, well, how about we just kind of use a, very aggressive notch filtering right at the stimulation frequency. Let's say it's at 130 hertz. Let's just kind of use, I don't know, eighth order or something filters and eliminate it. But that has some drawbacks, right? So one thing that we notice is, well, the artifact is really wideband, may not really be sufficient. And then also, in terms of flexibility, it's not great, because if you're probably notching this in hardware to be efficient, then the filter must match your stimulation frequency. So it doesn't really give you a lot of flexibility later on. And of course, here's another one that uses kind of a learning and template subtraction method. So pretty clever from the circuit's perspective, where what you do is you kind of learn the artifact over time, because you know when you're doing it, and then use a cancellation circuit to kind of inject the signal to cancel it out on the input. So ideally that would be great, because that would really reduce the dynamic range requirements of what you need. But in reality, I think for medical devices, it's really way too much overhead, because you have to learn the artifact every time you change amplitude or stimulation waveform. You're gonna have to learn it for every single victim channel. So if you've got, I don't know, 1,000 channels, okay, all of them will have to learn every time you change it, right? And then in terms of the circuit specifications are a little bit tight, is because the cancellation DAC has to be high enough performance in order to cancel that signal perfectly, right? And then ultimately, I think this is a huge concern, is that the artifact kind of must be quote, quote, learnable. So that kind of already implies that you're able to measure that artifact, which I don't think is usually a reasonable assumption. All right. And then of course, another one is like, hey, let's just kind of, make the best system we can with the best dynamic range possible. And then that will be the way we do it. But once again, I think what we see is that it's kind of a futile effort trying to record all of that at the same time. And then here's one last method that I think gets kind of overlooked, but maybe I'm just a bit biased, is blanking and interpolation. So in other words, like when the artifact happens, what we can do is we can quote unquote blank, or kind of turn off our recording circuitry, just don't take any data then, and then interpolate over the samples we missed, right? So yes, we're losing some data during that time. And then in terms of the circuit constraints, we need it to recover immediately after the stimulation event. So that would mean no residual artifact, only direct artifact. And using our modeling, we did show that is in fact probably the most efficient way to do it. And so here what you see is that we compare different methods. So using these high dynamic ranges, using notch filters, can we actually capture, reconstruct the original signal? So the original signal here is shown in blue. This is the power spectral density of some neural data that we recorded. And then the red signal here shows the high dynamic range recording system. And so even though this has no issue kind of, let's say, digitizing the artifact in our model here, you can see that it still corrupts the entire frequency band that we're trying to record. All right. And then we also applied a notch filter here shown in the black to see how much we can capture it again. And then over here shows the integrated powers for the beta band and gamma band, and how close those are to baseline are kind of the criterion for our success. So for a lot of these devices, we are looking for specific biomarkers. So typically, the amount or changes in beta band power or gamma band power, and use that to determine how to deliver our therapy. And so that's why these are pretty significant, is like, well, we don't want our artifact to kind of change what our the levels of our biomarker. So what we show here is that we are able to kind of faithfully reconstruct the signal using that blanking and interpolation here in the green signal. And yeah, of course, this looks very good here. And then, but sure enough, also in the integrated bands, the power matches quite well. And just to kind of make a long story short, we had to build the system. And so here is a circuit that we built that has 64 recording channels, and then also stimulation circuitry that can address any of those channels. And the original vision was that there would be several of these kind of neuromodulation ICs, integrated circuits, that would be put throughout the brain, connected to different types of arrays, right? And it was originally called Omni, Octopus Mimetic Neural Interface, but then we figured out people probably wouldn't like the idea of an octopus in their head. So we've changed the name, but also the vision has evolved a bit. But just to kind of briefly summarize what went into all this gargantuan amount of work is that the recording circuitry does something called memoryless sampling that really makes it amenable to this kind of interpolation method. So that means every sample is independent of the other one. Right? And the stimulation architecture uses precisely matched current sources. And the reason we do that is to minimize the residual artifact, right? Because that's pretty critical to that interpolation method. Because if you have that kind of long-lasting error, well, guess what? That's going to get interpolated, and maybe that's not so great. And so we really need a combination of these things to make it work. So we built it into a system called WAND, so wireless artifact-free neuromodulation device. We got lots of input and took a vote. So this is an entire system. So each little chip, we put two chips on the PCB. There's a FPGA field programmable gate array that provides kind of the system level control for the system. There's some memory. There's a Bluetooth chip on there so we can get some wireless communication. And then all of that was designed to fit inside of this thing called a microdrive, which is an array of these kind of needle electrodes that are then implanted into a non-human primate. And so here's kind of the cartoon of what we did. So the microdrive is up here, right, with wireless telemetry, so we can, relay data and commands back and forth. And so in terms of the task, what the monkey is doing is it was trained. I think this is part of the coolest thing. It was trained to control the joystick. And so what it does is it moves the joystick to control a cursor. So it gets a delayed reach task. So it's trained to hold the cursor position here in the middle. And then a peripheral kind of target will appear on the outside, kind of here. And then the monkey has to kind of move the cursor over there and then hold it. All right. And then once he does that, then this triggers like a solenoid and he gets a bit of juice, right? Because one thing I also quickly learned is that the monkey does not work for free, that he'll do it once or twice. So we do lots of trials, like after the juice runs out, but then all of a sudden he just stops cooperating. It's like, oh, what happened? It's like, oh, we need to refill the juice. All right. So yeah, I thought that was a lot of fun. Of course, I couldn't be in the same room. I had to watch through a window. So that was also a fun experience of trying to tell the animal people, like, okay, all right, try switching these wires, or like, oh, we need to switch the battery, and trying to debug some of these issues by just looking through a window. But here's also one of the cool things is that looking at that integrated beta power during one of these tasks, so we can identify kind of what's called the hold phase. So while the monkey's kind of holding in the middle, and then he's preparing to move, right? We can see an increase in beta power. And then we can very easily see the movement, right? Beta power drops, right? This is kind of a simple showing. Gamma power, of course, is kind of doing the opposite here during the movement. And then, of course, then you see the reward phase, right? That's, we don't actually have a true trigger for it, but we can actually see it from the beta band power. So what this is, and it's not clear to me, I think I get, or maybe the neuroscientists aren't completely sure, is that does the beta band power go up because of the reward or anticipation of the reward? So they don't know that, but either way, we can measure it with our system. So they move it to the successful trial. He's going to get juice. Dopamine comes out. He's very happy. And so here's some kind of power spectral data, just kind of showing open loop data. So the gray, if you can see it here, is just kind of baseline local field potential, neural activity. And then the red is when we stimulate. And so the red, this is with some of those mitigation issues already, like the precisely matched phases, memoryless sampling. Even so, you see it does corrupt kind of the spectrum, but then we do linear interpolation here in the blue on the FPGA, which is quite simple because we know when we're going to stimulate. We just have to save, to save this sample in memory, and then we'll just, kind of average it with the next sample. All right, so very efficient. And what we see is that we can faithfully reconstruct that local field potential. And so we did it in a closed loop experiment where where we would record from the M1 in the brain, and then we would actually do a FFT on that in real time. So we would measure the beta band power. Sorry, that font's a little small. And then also compute the derivative of beta power, just a slightly more robust. So that's also an active area of research. People are looking at, what are the most maybe robust biomarkers of movement or intention or things like that. And then after we would sense some kind of configured threshold, we would deliver stimulation. All right. And the purpose of this was just to replicate some work from the lab of Krishna Shenoy at Stanford done in 2007, where stimulating during that hold period before moving will actually, make sure I say this right, increase reaction time. So make them move slower, not improve reaction time. So what we do is in a closed loop way, we can sense from the neural activity when the monkey is in the hold phase, we deliver stimulation, and then sure enough, we see a large change in reaction time, right? Because we are in a sense, disrupting preparatory activity, right? Of when they're doing it, and then we compared it to just kind of randomly delivered stimulation, and we see a pretty significant difference in reaction time. So yeah, that's kind of one of the issues is now that we can enable closed loop, what do we actually do, with closed loop? And that's the hard part. And so our future directions is one thing we've partnered with a startup company to commercialize our closed loop chip technology that's going to be applied to as a memory prosthetic for people who suffer from traumatic brain injury. But it's probably not my place to spill the beans about that here. But it will be a very, very long process because it's actually meant to commercialize and become a medical device. And then locally, what we're doing is, we want to look at using some machine learning search strategies to optimize therapy for deep brain stimulation, so Parkinson's. So for that, we will use a Parkinson's disease model in rats, implant them with electrodes, and then use a closed loop stimulation method. So we'll see if I get an invite back in a couple of years. Hopefully I'll have some more updates and won't be as late next time. But for this one, what we'd be doing is we would want to compare it to a ground truth behavioral readout, like is our stimulation therapeutic? All right, we can actually see, how fast are they moving? What does their gait look like? Compare it with the neural data we're recording, and then use that to optimize our stimulation. So for that, right now our preliminary work is we're looking into using Bayesian optimization, and what we would do is use that to make an effective search strategy to find the best stimulation parameters. Right? And really the goal there is we want to converge quickly, just given the amount of tests we can do with the behavioral readout, right? So yeah, it'd be great if we could just blindly search everything and look at all 128,000 different possible combinations of stimulation. However, that is a lot of behavioral trials. So we have to be much more sophisticated in our search strategy. And one thing that will actually be, after we initially validate kind of the equivalence of neural recording and behavioral readout, we'll actually be able to search a lot more things using the neural readout as well. All right. So last, I just want to talk about this other project about miniaturizing implantable nerve stimulator called stem dust that uses ultrasound to power and control the device. And I do bring this up, not to be political, but maybe be a bit technical. So of course, lots of ideas going around that there are certain injections that will have little microchips inside them that will control you and do all sorts of things and track you, which I find a bit offensive because I'm very much trying hard to do that, and it's not as easy as they make it out to be. So first of all, it's powered at, using 5G, which is a very high frequency thing, inside a 22 gauge needle. So you have really like a 400 micron inner diameter. So while I can make little systems for recording and stimulation that are on that scale, there's this pesky thing called physics that keeps me from powering and communicating with such a device using 5G at those scales. And so for that reason, we're investigating ultrasound as a means to power and communicate with these devices that are implanted inside the body. And there's a few advantages of why we're, one is kind of just how much that attenuates into tissue. So ultrasound sees a little bit of attenuation as it goes into the body. However, kind of radio frequency waves can see quite a bit, particularly at high frequencies. And so one example I give is, think of putting maybe something in a microwave. If it's meat, it doesn't heat evenly, right? The core will be cooler than the outside because the waves go in there and attenuate, right? And so if we want to use something similar to power devices, we'll have the same challenges. The outside will get cooked before we power our deep implant, which is kind of not what I had in mind. And it's only going to get worse as you transition to these higher frequencies, right? The skin depth and attenuation is just so much higher. And then relatedly, because of that attenuation, and potential danger to the body, the intensity limit set by the FDA for ultrasound is significantly higher than it is for RF. So we have much more available power to use with ultrasound. And somewhat relatedly is that the wavelength is a bit different. So that just means how efficient can we make an antenna that works on these scales. So RF will have a much larger wavelength, like 32 millimeters, compared to ultrasound, which will have wavelength that's below a micron. So we can actually make microscale devices. And then one other advantage of ultrasound is we can use the backscattered acoustic field as a form of readout. And so what this means is as kind of incident ultrasound hits these piezo crystals, some of it will get bounced back. And how much gets reflected is based on the electrical load seen by that crystal. And so that means is an open circuit, it will reflect a lot, and a short circuit reflect very little. And so what we can do is we can modulate this resistor, RE, to kind of change what gets reflected back and use that as a way to communicate with our external controller. So here's the system that we built, right? So it consists of a piezo crystal. So this is, I think this is 750 microns on the side, it's a cube, and it converts acoustic ultrasound waves into electrical power that we can use. And then there's an integrated circuit. And its job is to, one, rectify that power, so turn it into a DC that we can use. And it also makes the implant smart. So it will facilitate, okay, this is how I'm going to stimulate, with how much and where, right? There's a local capacitor there for some energy storage that we're looking at getting rid of course, to shrink the device. And then here's just a little bit of a, neural interface stuff where we use electrodes that are coated with a specialized conductive polymer, P.PSS, to improve, how much, in a sense, a voltage we need to stimulate with, right? Or a voltage that we need to burn to stimulate the specific current. So here's just a photograph of one of the early prototypes, and we conventionally make it a lot smaller, to fit it inside the ear next time, right? And then here's the architecture of the system. So the top here, in a sense, shows the kind of ultrasound coming in and hitting the piezo crystal here. This is how much backscatter we receive. And then this is the architecture of the chip. I'll quickly walk through it just to give you some idea of what kind of things we can, what kind of complexity we can put into a very small chip, small system. So kind of initially, it starts off with a power up phase where, ultrasound comes in and it just kind of powers up the chip, right? Things reset, make sure we're starting in the right state. And then there's a gap in the incident ultrasound. So we just kind of turn it off on the outside. And what that gap does is, depending on how long the ultrasound is off, we use a time to digital converter to convert that into an amplitude, right? So in other words, like the longer it's off, the higher our amplitude is in this case. So we're also sending data here that is kind of encoded by the time or the duration of that phase or state A1. And then when ultrasound comes back, there's a short kind of header packet or something for things to wake back up. And then we deliver a stimulation pulse through here. So we push current through the stimulation electrode and sync it into the return electrode. And at the same time, we also modulate this switch over here. So as I mentioned before, we can change the resistance seen by the piezo crystal to change how much gets reflected back. And so what that does is it will give us some data saying like, hey, I'm stimulating, everything is good, everything's compliant. Right? All right, and then there's an interface gap, which really the only purpose of this is to stop stimulation, and then more on the kind of electrophysiology side is that this has been shown to be biologically significant, that you can actually change stimulation thresholds by changing the duration of this. But just keep in mind that while you're doing this, the electrode is just holding charge. And then we go to the recharge and short phase, where we're kind of recharging that storage capacitor, and we're also clearing any charge that we had on there from stimulation. Because if you don't clear it, then it'll build up and generate all these chemical reactions, and bad and terrible things will happen. All right. Okay, so to test this in vivo, what we did is we took our device and we affixed it to the sciatic nerve of a rat. We have this kind of external setup, just using a commercial ultrasound transducer, that you would use to, like the ones you'd go and, get an ultrasound, image done with, use that to control our system. And what that means is when we stimulate the sciatic nerve with kind of enough charge, it will, propagate down the nerve and force, hind limb muscles to contract, right? And after they contract, what we'll do is we'll measure that with, we can actually measure that activity itself with EMG amplifiers, so electromyography. All right. Okay, so hopefully people aren't too squeamish. I keep this a bit short, but really just showing that it does in fact work. So here's the implant mode on the sciatic nerve here. So you can see that's kind of why we designed it to be that size, as we designed it for our initial thing here. And then, okay, I'll play it again. So here's, I think I sped this up a little bit, but like just showing that we can get regular stimulation wirelessly delivered. Then reviewers were like, well, that's not truly implanted. And so then we did this other one where we actually did close the skin flap, and show that we do, in fact, are able to stimulate wirelessly, or wirelessly power the system to stimulate in that fashion. And here are different EMG readouts. So one huge advantage of our system is that because of the way we're controlling it, we have really high temporal precision. We can get kind of arbitrary pulse widths. And so here's just EMG responses for different pulse widths that we stimulated with. All right, and then here is where we're stimulating with different currents. And you'll also notice that these are actually, there are several trials on here, so there's some error bars. And really the point is that we have a wireless device, and because of the way we're able to control stimulation is that we're delivering a repeatable charge every time. And so one thing I didn't want to mention is that we can do this deeply implanted in tissue. Of course, that's, rats aren't that big, but we have tissue phantom on top to show that we can actually put things, say 7 centimeters into tissue and still power them and control them. And then it's precise and well-controlled stimulation, right? Very repeatable, right? Not sensitive to received power. And then ultimately it's very small volume. So trending toward a microliter size device. And we think we can just get it, quite a bit smaller. So kind of on that note, what we're working on now, our kind of next target is integrating solutions from both of these projects into one device. So multiple channel implant that's 100 nanoliters or less, and able to precisely target fascicles within a nerve. And so that's really our vision for the next generation of bioelectronic medicine. All right, so with that, I'll conclude. Once again, remind you of the merits of bioelectronic medicine. You know, it's targeted therapy. I think we can deliver therapy with fewer side effects, can be immediately effective. And then I think the big one in my mind is it's closed loop. So that will enable us to do patient-specific therapy and really reduce side effects and clinician burden. And of course, I'd like to thank my graduate students, so Tala, Mehdi, and Shama, who helped me with some of this work, my collaborators at UC Berkeley, and of course, some funding agencies that have helped support this work. All right, thank you.